This is lecture number 15 of the course AU203 Statistics and Quality Control. In this lecture, we already have done binomial distribution. In this lecture, we will go into another discrete distribution called hypergeometric distribution. We start with hypergeometric distribution, and then we will compare hypergeometric and binomial distributions because both are discrete distributions. So we will look into the case of multivariate hypergeometric distributions, and then we look into the formula for calculating the mean and the variance of hypergeometric distribution, and in the end we will look the same thing in using Minitab as well. Okay, let's say you have a box having 6 red balls and 14 yellow balls, and what you are going to do is you are picking 5 balls at random and without replacing it. So once you pick one ball out of from the box, you are not replacing it back. So what is the probability of drawing exactly 4 red balls? So you have altogether 5 sample to be picked, 5 balls to be picked in the sample, and you have altogether 6 red balls, 14 yellow balls. So altogether there are 20 balls in a box. So once you pick, if you see this problem is, if you think the unknown here is calculating the probability of red balls. So you have altogether 6 red balls and you are picking 5 red balls. You are picking altogether 5 balls. So what is the probability that you are getting 4 red balls? It means your random variable x would be, if you take it, getting the red balls. And the value of the red ball, value of the random variable here is exactly when x equal to 4. So if you think that variable to be a binomial random variable, then obviously it is not satisfying the condition. It satisfies all other conditions, but the condition of being independent a trial is not satisfied. So we cannot use binomial distribution to carry out this probability. Okay, how we calculate? Let's say once we are picking 5 balls and we need to pick 4 red balls out of that 5 balls. So it must be, one ball must be the yellow ball here, because you are need to pick 5 balls, and out of that 4 must be red balls. So then probability of getting exactly 4 red balls would be, total possible events is you have 20 altogether balls, and out of which you need to pick 5 balls. So 20 combination 5 would be in the denominator, which represent the number of combinations of choosing 5 balls out of total 20. And in the numerator, the number of possible ways of getting your event is to pick exactly 4 red balls. So altogether you have 20 balls, out of which 16 are red and 14 are yellow. So the first you pick the red balls, so your 4 red balls is being chosen out of 6 red balls. That would be the number of combinations, and then obviously you need to pick 5 balls, so 1 ball must be from the yellow. So you have altogether 14 yellow balls, so 14 combination 1. So if you multiply that, you will get the numerator of that probability, and this way you will be able to calculate. So it's 1.35% is the probability. Out of these 20 balls, you pick 5 balls and exactly 4 balls are red. So it is quite a small probability that your out of 5, all 4 are red balls. Out of 5, 4 are red balls and 1 is yellow ball. Okay, let's say if we just change the scenario. For example, you are picking this time also 5 balls, but this time you are interested in exactly 3 red balls. So it means there would be, if you're picking 5 balls and 3 are red, then 2 must be the yellow balls. So probability of getting exactly 3 red balls means the numerator remains the same, 20 combination 5, and the red balls would be 6 combination 3, because this time you need 3 red balls out of 4, and 14 combination 2 would be the by which you can choose the yellow ball. So this time you see the probability has some bigger number. 11.7% is the probability that if you have exactly 3 red balls. So here what we can do is we can formalize this experiment. What we are doing is we are randomly sampling n objects out of total capital N population. So capital N represent here the number of items in a population. From the previous example, it was 20 balls. So N, capital N would be 20, what your population size. And here the sample size is small n, and you are picking in the previous example 5 balls. So 5 balls would be representing n. Okay. And what we are doing is we are not replacing it without replacement. So from a source that contain A successes, A is the number which is in the first case we are take that A would be 4. 4 red balls we are interested in. Then obviously not having red balls would be the total number n, which is total number of objects. By subtracting it, the number of events or the number of successes, that is in the previous problem the red balls. So out of this total n objects you have, so this the same scenario can be generalized, and let's represent x as your random variable, and obviously it's a discrete distribution, so it's a discrete random variable, and the mathematical function which allows you to calculate the corresponding probability for that discrete random variable would be called as probability mass function. So in that case we can represent x as a random variable which can take any values. The value of that random variable is small x, and here you have n objects and you are picking a sample of small n objects. So out of total capital N, you have small n is your sample size, that is in the denominator, and the number of objects of your event for your success is A, and here we are interested in total, let's say in previous problem 6 red balls, so A was the 6 here, and we are picking let's say 4 red balls, and the 4 would be the value of x. And here obviously total you have A success events, so number of non-events or the failures would be, if A is a number of successes, then n minus A would be the not having this A event, not or in this particular case not having the red ball, so maybe some other ball. So if there are 2 types of balls are present, the number of outcomes is exactly the same as binomial distribution, where you have a success or not having a success. So if it is not having a success, it will be called as failure or not having your event. And you need to pick n minus small a. Small a is the number of successes, and out of that the sample size, once you have n sample size, so x you already have picked, now you are available with n minus x. So as we know, capital N is actually the sum of a plus small n, and so the capital N would always be a number, would be to the total number, and n would be always be smaller than this total number, and number of successes would always be either equal to or smaller than the total number. The question about x, the value of x can take a value between this, and this value you can work out. Either you take the maximum of that, because if this number comes out to be negative, then 0 would be the maximum of that. So the value of x, which is you are interested in, that would be between this value and minimum of a and n. Whatever the value of a and n is smallest, that would be your this number. So the value of x can range from this to this. Okay, here x is the number of events in the sample, and the hypergeometric distribution is, we can think of a three parameter distribution where you are drawing samples from a population, and obviously capital N should not be a big number, otherwise you cannot calculate its combination. So for relatively small size population, you can use this distribution to calculate the probability where you are not replacing an object. In binomial distribution, we were replacing an object so that our each in the probability of getting your required required number is independent of the number of tries. In hypergeometric distribution, it is different. We are actually not replacing it. So probability in the next trial would be different from the previous trial. So it is a non-independent case actually. Okay, so in short, we can write down x is a random variable, which is h is just representing hypergeometric distribution, and it has the parameters as the population size, capital represented by capital N, and small a is the number of successes or number of events you are interested in out of a sample of small n, and n becomes your sample. And let's say if you want to see its distribution for this previous case where you have 20 balls, and you, let's say here the sample size is not the same, it's actually, let's say if I take it at 10 is the sample size, and 2 is in which we are interested in. So at different values of x, for example here 2 red balls, let's say, then out of 2 it could be 0, it could be 1, it could be 2. So if your this number is changing from 2, then you have this distribution, because it could be 0, it could be 1, it could be 2. Or here if it is, this number is 4, then it could be 0, 1, 2, 3 and 4. Or if it could be 6, then it could be 0, 1, 2, 3, 4 and 5 and 6. So as you see, is this number is m is growing, where which is actually the same as a actually in our case. Then you see the distribution is becoming spread out, and the shape is in this particular case is like the same as binomial distribution, or as well as a symmetric one, because when your probability is 0.5 in your binomial distribution, it is always a symmetric case. So depending upon these parameters, the shape of the distribution would be changing. Okay, let's say do another example in which, suppose you have a large school has about 2000 students, out of which 1100 are female and 900 are male students. So you just take a sample of 10 students. What is the probability of getting exactly 7 of these students are female? So once you have to find out, then obviously the total number capital N is 2000 here, and the sample size drawn is 10, and you are interested in only the students, 7 of those selected would be female. So you are picking up from 1100 female students. So in the and you can see that these parameters for your x could be your random variable, which could be the number of females. If x could be 0, x could be 1, x could be up to 10, up to 7, x could be up to 7. So you are interested in exactly 7 female members. Here, let's say if you use your probability mass function to calculate the corresponding probability of getting exactly x equal to 7. So you have altogether in the denominator 2000 students, and you need to pick 10. And out of 10, you are interested in having all 7 to be females out of 10. So 1100 are females, and choosing 7 females. and obviously those males would be out of 900, 2000 minus 1100, that would be 900, and out of 900, 3 would be obviously would be your male students. So 7 female, 3 male, that would be the altogether 10 is going to pick. So if you calculate this combinations from the calculator, so you end up with the probability that 16.64% is the probability that you have 2000 students, 1100 female, 900 males, and you pick a sample of 10, and you are exactly getting 7 students which are female, and obviously 3 would be male students. Okay, let's say if we try to solve this problem using a binomial distribution. In binomial distribution, we know that what we are interested in the number of females selected. Let's say the probability of getting a first female would be, for example, you have 2000 population, and out of 2000, 1100 would be female. So first female picking would be, first female in the sample would be 1100 over 2000, or 11 by 20, or 55 would be 0.55 is the probability of success, that is picking the female students. So if I just make it as 0.55 is my probability of success, and number of trials would be 10, and probability of getting exactly 7 females would be 10 combination 7, and probability of success is 0.55 to the power x, and 1 minus probability of success would be probability of failure to the power 10 minus 7. I got this probability. As you see, this number is different from this number, so it means there is some variation, but at least up to the 16.6 first decimal digit, you can see that the numbers are exactly the same, but afterwards it is different. So it means the same problem if your n is large, capital N is large population, relatively large population, so you can use the binomial distribution to predict the same. But obviously this is not the correct representation, and the difference is just because of the fact that once you in the large sample of 1100 female students, probability is going to change. If you first is female, then the number of females has been reduced. So once you are replacing it, so you are having the same probability, but once without replacement, your probability is going to change. That's why these two results are different. Okay, so from this particular example, we learned that we can use binomial distribution even to evaluate the probability even for a case of without replacement. And that is the case of using the hypergeometric distribution. And as a thumb rule, as a rough guideline, if we are not sampling more than 5% of the population, let's say here our population is 2000, and we are just sampling 10, then this binomial approximation provides a reasonable approximation to this hypergeometric distribution. Let's say our 10 out of, if you're 10, so it is only 0.5%. So that's why, for example, if it is the probability of fourth female, so it means here once you pick the first female, then the total number of females has been reduced, which would not be 1100 but 1097 out of, and the total population will also be, once you are not replacing it. So approximately your even for the fourth female would be 4% chosen to be female. This probability is approximately near about 0.55. If it is not going to change, probability of success is not going to change, then you can use binomial approximation for this situation as well. Okay, so what we do is if your sample is small n, which is relatively smaller than the population, Then the correction is small, and hypergeometric distribution gives you the same result as binomial distribution. And we can see that, for example, here your even for a population of 50 and your sample size is 5, you see when you pick 0, you pick 1, 2, 3, 4, and you see that this line is representing the hypergeometric probability and this is representing the binomial probability. So, and you will see there is not much difference. 3 2 and 3 1, and this 3 2 and 3 1 is 15% is also about 15%. So once your sample is taken from a population, it is relatively smaller sample, less than 5%, then you can use the binomial distribution to predict the case in which even you are replacing it, just like binomial distribution. So for example, you have a batch of 100 parts taken from a local supplier and 200 from a foreign supplier. So altogether your population is comprising of 300 parts. So what you are going to do is you are picking 4 parts are selected without replacement. So this keyword clearly indicates that without replacement means your probability doesn't remain the same. So you cannot use binomial distribution. So you need to use hypergeometric distribution. So what is the probability that they are all from the local supplier? So let's say X is the number of parts in the sample from the local supplier, and which is a random variable. And here the parameters are 300 is capital N and A is 100, which is there are total 100 parts from the local supplier and we are picking only 4. And the probability of getting exactly 4 would be 3 combination 4 in the denominator, and in the numerator out of local supplier 100, and not local means out of 300 it would be 200, and you are not picking any part from the foreign supplier. Then this would be the probability that in this 300 parts box you are picking 4 parts, and all these 4 parts coming from a local supplier is 1.19% is the probability. Okay, what is the probability that 2 or more parts in the samples are from a local supplier? Then 2 or more part means X should be greater than and equal to 2. So it could be X equal to 2, it could be X equal to 1, or it could be X equal to 2. You add all these probabilities to get your required probability. And if let's say your supplier says that at least one part in the sample is at least 1 means X must be greater than 1, or greater than equal to 1 means 1 minus probability X equal to X is less than 1, and less than 1 means probability when X is 0. So 80.4% is the probability that at least 1 part or 2 part or 3 part would be from the local supplier. So the same rules for probability can be used for calculating the probability in hypergeometric distribution as well. Okay, now let's look at this idea of because you have 2 groups of people, either in the previous case whether you have a red ball or a yellow ball, or in this previous problem whether you have a faulty equipment or component or not a faulty component, or you have a male and female. If you just have these 2 scenarios, because that is where the binomial random variable works, because either you have a success or either you have a failure, so you don't have any other thing. But in hypergeometric distribution this idea can be extended to more than 2 variables. For example, here we need to form a committee which involves 12 persons from Democrat Party, 24 from Republicans, and 8 are independent member in the committee. So out of all these you need to pick a committee of 6 members, and the condition here is what is the probability that out of 6, 3 are coming from Democrats, 2 are from Republicans, and 1 is from the independent sample. So the same probability mass function we have extended the idea. So 12 plus 24 plus 8, altogether you have 44 people, and you need to pick a committee of 6. So 44 combination 6 would be in the denominator, and out of 12 we need to have 3 Democrats, and out of 24 Republicans we need to have 2 Republicans, and out of 8 independent we need to have 1. So we have extended this idea to more than 2 groups. So or if you have more groups, you can extend this idea. So this is actually called as multivariate hypergeometric, and keeping in mind how you're picking a committee of 6 members and you're not replacing it without replacement. So the key about this finding out whether it is a hypergeometric distribution, then there is a word is without replacement. Okay, now we can easily calculate the mean and the variance of this hypergeometric distribution. If x is a random variable, hypergeometric random variable with the population n, and n is small n is a sample size, and a is the number of elements where you are interested in, or having a success or having an event. So its mean would be exactly the same as n times p. P is the probability of success. For example, total out of n, a is the number of events which you are interested in. So that is exactly the same as the formula for we have worked out for calculating the mean of the random variable, expected value of a random variable, where x is a hypergeometric random variable. A and n, so it is exactly the same. This a over n is nothing the same as p. So np is the probability of expected value of a random variable, which you already have proved in the previous lecture. And variance is the same as npq. So n is this, p is this, 1 minus p is actually q, and here just this is a correction factor for using the fact that in this so this is capital N minus small n divided by n capital N minus 1 is actually a correction factor for a fact that you are actually NPQ is the formula for binomial, where you are not replacing it, you are actually replacing it, but here it is without replacement. So this is the correction factor for without replacement, because your population is finite here. For example, a batch of 400 parts, same thing, same problems. So here your random variable is this, and the mean is 1.33, and the variance is 0.88. Just bringing everything in the formula to get the mean and variance of this hypergeometric distribution. Okay, the same thing we can do it on a Minitab, and that is what we will do it. Okay, let's see how we can do hypergeometric calculating hypergeometric distribution probability or through of hypergeometric distribution using Minitab. Let's say, for example, I go to this calculate and here my probability distribution. So I can pick hypergeometric is that. Okay, so once I pick hypergeometric, I get this tab. I'm interested in calculating the probability. Okay, let's see. We have the problem of the first problem we did is we having 6 red balls and 14 yellow balls. So population was 20, population size was 20, and we have picked a sample of 5, and we are interested in calculating the red input is actually the red balls, and there were altogether 6 red balls. So event count in this population is event is having a red ball as an event or a success. So here this capital M is representing what we used to represent in the theory with A, letter A. So capital N, A and small n, capital N and small n are exactly the same. Okay, input constant, for example, we are interested in calculating the probability at x equals to 4, exactly 4 red balls. Okay, if I do it, if I click OK, I will be able to see the corresponding probability in the session window. So you can see when your n is 20 and m is 6 and n is 5, so the corresponding probability is 0.013459. So this is exactly the same as if you see this problem 20 combination 5 and 6 combination 4 and 14 combination 1, you end up with 0.01354. So if you have to calculate for exactly for the 4 red balls, then you do the same thing, just go to the calculate probability distribution, picking hypergeometric, and here let's say you're interested in for exactly 3 red balls. So the problem is the same. I can get it. So probability comes out to be 0.117389. So it is exactly the same as this we have calculated, 0.117389. Okay, as I told you that you can see for this particular problem, you can shape of the distribution you can work out through Minitab. It's quite simple. Go to the graph, probability distribution plot, and here you want to see the varying different parameters. Let's say you have a distribution, they're selecting the distribution like hypergeometric. Okay, let's say we take the same population size, even counts in the population is 6 red balls, and let's say the sample size is 5. And for example, instead of varying the parameters, so let's say if I vary the parameters like 2, 4 and 6, not exactly 6 but 2, 4 and 6. Let's say if you have 6 red balls, or maybe make it some bigger number. So if I just do it and I want it to have on separate graphs, let's say I want it on a separate graph, then I will show you how to use the lay editor once you have a separate graphs. Okay, I just click on OK. So for that particular thing, I will be able to get for different values of 2, 4 and 6, if there are 2 red balls or 4 red balls or 6 red balls, or maybe if I just forget about 4, I just go with the 4, 6 and let's say 8. So I just click on. So I can have 3 different graphs on a separate graph. So the good way is to compare all these 3 graphs. Just go onto the editor toolbar using a layout tool, and here you have all these, for example, 3 rows and 1 column, let's say you have. And what you want is this graph to be on this side for 4. And this one you want it, let's say for this one for 8, 6 and 4. So just finish that. By doing that, you will be able to see all these 3 graphs on this scale, and you can just make it bigger in size. Let's say this distribution, this annotation rather, and then we can see that for different values, 4 it is different, 6 it is different, 8 it is different. So there would be a different distribution associated for once you change that parameter, because you know hypergeometric distribution is 3 parameter distribution. So I have just kept these two fixed and vary this parameter in different graphs, and the same graphs can be plotted like that. So this is how we can use this layout tool. Okay, so I'm not going to save that and just bringing all these, minimizing it. Okay, what else I can do is, for example, if we have a situation like this in your lecture, let's say comparison. So we have a comparison of hypergeometric distribution and binomial distribution. So this we can do it quite easily in this Minitab. Go to the graph toolbar, probability distribution plot. Let's say I want 2 distributions to compare. So just select 2 distributions, and here let's say I have a binomial distribution with number of trials 5 and even probability is 0.5, and we have a hypergeometric distribution where population is size is 50 and event count in the population that we are interested in is 25 and sample size is 5. So both have the same sample size. Here So if I just say multiple graphs, so I want to see these graphs, let's say, in separate panel of the same graph with same x and y. So if I just click it, I will be able to compare these two types of distributions. So I can see almost the same probability you are expecting it, whether you are using this binomial distribution or hypergeometric distribution. So sample size is 5, sample size is 5 here, and here it is three parameter distribution, this is two parameter distribution, and we can compare it side by side, their probability distribution plot for both distributions. And you can have the same sort of thing is, let's say I don't save it, I just go to this probability distribution, and instead of separate panel, if just I wanted an overlaid on the same graph, so this is another option which you can do is, if you do that, and then you can see this blue one is your binomial distribution and the red one is your hypergeometric distribution, and for different values from 0 to 5 the corresponding probabilities are here. For example, this hypergeometric distribution, it is 0.14962, and for binomial it is 0.15625. So there is a very small difference between these values, and you can see it, we have done it in theory for 0.156 and 0.149. So exactly the same thing you can compare two distribution plots. So this is quite handy, Minitab doing it, and you can verify your answers. For example, let's say we solve this problem of this one as well. For example, a batch of parts for 100 local supplier and 200. So altogether capital N is 300 here in this case, and we are interested in local supplier. Local is 100, and we are having a sample of 4 samples. So if you look back this previous graph comparing binomial and hypergeometric, as you have seen that if your sample size is 5, which is smaller, so you don't see much difference between binomial and hypergeometric. But if let's say your sample size is much bigger, it is actually 5 out of 50 is something is compared with 50 small sample size. But what I do is I just compare it the same thing, the two distributions, but in this hypergeometric, let's say my sample size is, instead of 5, I made it 50, and I want to see the same thing again. So now you see there is a big difference between probability of binomial distribution and probability of hypergeometric distribution, because sample size here is much bigger than the previous case. In previous case we have only 5 sample size, and here it is 15 sample size, and you can see the difference. The two distribution plots are quite different. So this approximation of binomial, which requires replacement, and hypergeometric doesn't require without a replacement, only works when your sample size is smaller, and this is, you can understand it from this graph as well. Okay, going back to this problem, you have this problem. This problem can be solved as well. For example, we try to solve that problem using for example, what I do is I solve it little differently, because instead of getting a one value, let's say I'm interested in getting different probabilities. So first go on, okay, I don't copy, I don't, okay, so just need to save it. Let's say my x is here, some values, so I got 0, 1, 2, 3, 4. I mean, I have 4 possible samples, and I'm interested in calculating the probability using this. I can do it like that. For example, calculating probability distribution. So I'm using hypergeometric, and here I'm interested in calculating the probability with my In this problem, we have 300 parts altogether and 100 parts from the local supplier, and we are getting 4 sample size. And let's say for my input column is C1. I mean, this is where I want it, and C1 simple. C1 would be enough, and output storage would be at C2. So all these corresponding probabilities would be stored in the column 2. Okay, so let's I do this. If you check it out, so you got this probability for x 0.1956 for example, in the first part x was exactly 4, so 0.0119. So x was 0.011854. It is exactly the same as like we have calculated. So it is x equals to 4, and when x equals to 0, we know that when x is greater than or equal to 2, so it means it is a cumulative probability. So we are interested in calculating this probability. We can do it through graph as well, or we can do it through table as well.